Welcome to the lecture on parametric programming. This happens to be the extension of linear programming problem, particularly extension of Simplex. One extension of Simplex we have seen in the form of sensitivity analysis. Some of the concept of sensitivity analysis will be useful in understanding parametric programming. If you have not, if you are unable to recall some of the concept, we will try to recall them at the time when we come across that point, right? So what is parametric programming? Parametric programming is a linear or non-linear programming problem in which there exists a parameter in addition to a decision variable. Parameter is a variable like time or angle which increments in a controlled way. In simple terms, it is a variable which is used at the place of constant, which then can be varied. For example, like the coefficient of x1 is 10. So what I can do, if I want to vary it in a controlled way, then what I can do it like I have done here, 10 minus 2t. So as values of t will go on changing, the coefficient of x1 will go on changing. So I am getting the effect of constant also, and I am able to vary that constant the way I want. Okay, that is the parameter that differentiates variable from parameter. So this problem maximize z equal to 10 minus 2t into x1 plus 5 minus 3t into x2 subject to 8x1 plus 2x2 less than equal to 48, 2x1 plus 4x2 less than equal to 24, and lastly x1 x2 greater than equal to 0. This part, particularly constraint part, you have seen as normal as you have seen earlier in LPP, right? But the objective function which you are seeing here, it was normal to see that as 10x1 plus 5x2, but we are having the inclusion of one more variable there, like it is 10 minus 2t into x1 plus 5 minus 3t into x2. So t is doing the job of variabilizing this constant coefficient, variabilizing the coefficient. Okay, so we are going to carry out parametric analysis of this problem. Parameter in this problem is t. We will be finding the solutions to this problem at varying values of t. Okay, so I hope you have understood what parametric programming is. All right. So now what I will be doing, I will be taking t is equal to 0 for if I want to solve this problem by simplex method, I will be taking t is equal to 0 because I cannot solve this problem by simplex method by carrying t into simplex. Okay, I will have to take t is equal to 0, then only it will be possible for me to solve this problem. So this problem which I am going to solve by simplex method is going to be 10x1 plus 5x2 because I have taken t equal to 0 and this constraint which are in front of you, right? So I have the simplex solution of that problem, right? I need not explain how I solved it by simplex method, right? This is the first simplex in which I have tabulated the problem by including the slack variables in first and second constraint. I have then tabulated it and then iteratively improving the solution. I finally got the optimal solution, x1 equal to 36 by 7, x2 equal to 24 by 7. This is optimal because all Cj minus Ej's are less than equal to 0, and the value of Z optimal value of z comes out to be 480 by 7. So I could get the solution to the simplex method by taking t is equal to 0. Right? Now that I have got the solution, I will restore back this coefficient to what those are given in the problem. 10, I will be replacing it by 10 minus 2t, and 5 I'll be replacing it by 5 minus 3t, because that is the actual coefficient of x2 in objective function, and 10 minus 2t is the actual coefficient of x1 in objective function. So wherever there is x1 and x2, I will be replacing their coefficients to 10 minus 2t and 5 minus 3t respectively. So here also I have replaced their coefficients. Okay, this values are same as you are seeing. Okay, but now Cj minus Ej, I will be finding them afresh, because these values, coefficients of x1 and x2, are now not 10 and 5, they are 10 minus 2t and 5 minus 3t. Okay, so you know how to compute Cj minus Ej, so I did that here. Okay, this multiplied by this will give you Ej, and this is Cj minus Ej. In this case it will be 0. Okay, for x1 and for x2 it will be 0, because x1 and x2 are basic variable, but for non-basic variable you will have to find that out. So 0 minus 0 minus in bracket 10 minus 2t into 1 by 7 minus 5 minus 3t into in bracket minus 1 by 14. I'll get this Ej. Similar way I'll get Cj minus Ej for S2. I will get B value, Z value, not B value, Z value, by multiplying this B values with this CB values, right? As we had been doing this in simplex method, right? Now the question is, for how long this solution will be optimal. What solution? X1 equal to 36 by 7 and X2 equal to 24 by 7. That appears here also. How long this is going to be optimal? That's the question. So very simple. As long as all these values are less than equal to 0, this will be optimal solution. Simple, right? All this value, this is 0, Cj minus Ej for x1 is 0, for x2 is 0, for s1 it has to be less than equal to 0, for s2 also it has to be less than equal to 0. So what I did, minus 15 plus 10 plus t by 14 is less than equal to 0. So by that I get t must be less than equal to 15. Okay, for this value to be less than equal to 0. And now I am concerned with this minus 10 plus 10t divided by 14 also has to be less than equal to 0. That means minus 10 plus 10t has to be less than equal to 0. That means t has to be less than equal to 1. Okay, so for this to be less than equal to 0, the allowable value of t is 15. But for this to be less than equal to 0, for this to be less than equal to 0, the allowable value of t is 1. If t exceeds 1, this will become positive, right? So this solution is optimal, that is the x1 equal to 36 by 7 and x2 is equal to 24 by 7 is the optimal solution from the time t is equal to 0 to t is equal to 1. Alright, now the question obviously will arise, what will be the solution when t exceeds 1? So what I will be doing now, I will be substituting the value of t is equal to 1 and I will be rewriting this solution. Just see here, my value will be here 10 minus 2t means t now is 1. So this will become 8 and this will be 5 minus 3 into 1, that will become 2. Same replacement here, this is 8 and this is 2, rest other thing same. Alright, so let's see here. Oh. So 8 2 I spoke about just now, 8 2 is here, rest solution is same, and Cj minus Ej you can find by putting the value of t equal to 1 in previous thing you have seen, or you can find them right here. Cj minus Ej for x1 and x2, as I told you, as they are basic variable, Cj minus Ej for x1 and x2 will be 0. For S1, let's find it. 0 minus 8 by 7 minus 2 by 14, that is 1 by 7. Okay, 7 by 7. So 0 minus 1, that is minus 1, and here it comes 0, but I am not writing it at 0. I am writing it at 0 plus, because little increment in the value of t will make this positive. Okay, so this has the tendency of becoming positive. So I am writing 0 plus there to signify that if t increases, S2 has the opportunity of becoming the entering variable. S2 will be entering variable. So when S2 is becoming an entering variable, I need to find which variable will become living variable. So for that, I need to find the replacement ratio B by key. This is the key column. So 36 by 7 divided by negative, so it will come dash, because the replacement ratio is not negative. All right. Then 24 by 7 divided by 2 by 7 will get you 12. So this is the only positive quantity, and therefore x2 will be the living variable, and in place of x2 will enter s2. So with that consideration, I have modified this table and I got x1 as 6 and s2 as 12. And all Cj minus Ej values here are Cj minus Vj value. This is Z value. All Cj minus Ej values are coming less than equal to 0. That means this is optimal solution. Okay. At t is equal to 1 plus, this is optimal solution. X1 equal to 6 and S2 is equal to 12. Now you just think, because the profit is decreasing as the time is increasing, okay, profit coefficient of x1 was 10 minus 2t. So after 1 week, if at all we are producing, then the chances of producing product A with which X1 corresponds are more, because it is giving you more profit in spite of the fact that 1 week is over, one time period is over. Okay, but the profit per unit of product B for which X2 stands has reduced to 5 minus 3t, means has reduced to 2. So we are our solution is of a kind that we are having we will be producing units of product A but not units of product B. We will let some capacity to go west. Okay, so optimal solution, all in all, what I am getting is x1 equal to 6, x2 is equal to 0, as you are seeing here. Again the question arises, how long this will be the optimal solution? How long this solution after t is equal to 1 will continue to be the optimal solution? So for finding that, what I need to do, I will have to replace this 8 again by 10 minus 2t, 2 by 5 minus 3t. This 8 also I have to replace by 10 minus 2t, and here it is S2, so the coefficient of S2 is not parameterized, it is 0. Coefficient of x1 is parameterized. Rest of the things in this row and this row are same, but because I have here 10 minus 2t, my Cj minus Ej value will appear like this. Okay, for x2 it is pi minus 5t by 2. For s1 it is minus 5 plus t by 4. So for this to be optimal solution, these values have to be less than equal to 0. So what I am writing here, pi minus pi t by 2 has to be less than equal to 0. Right? And that implies that uh, t has to be greater than equal to 1. Okay, when I solve this, pi minus pi t will have to be less than equal to 0. That means t has to be minus t has to be less than equal to 1. That means t has to be greater than equal to 1. And by this minus 5 plus t by 4 has to be less than equal to 0 implies that t has to be less than equal to 5. That means this solution is optimal within range 1 to 5. Till fifth week, this will be the optimal solution. Okay. And what will be the optimal solution? X1 equal to 6, X2 equal to 0. Okay, is valid from t is equal to 1 to t is equal to 5. Now the question once again arises, how long will this continue to be the optimal solution? So what I will have to do for that, I will be replacing this t by 5, because once again when t is equal to 5, how my simplex table will look like, that I will have to see. So this 10 minus 2t, t is 5, this will become 0. 5 minus 3 into 5, that is 5 minus 15, this will become minus 10. Okay, rest of the thing as those as you are seeing. So just look here, this is 0, this is minus 10, here it is 0 because the coefficient of x1 is 0, s2 was already 0. This you may find once again, like ej here is coming out to be 0, here it is minus 10, this is going to be 0 plus, because we saw that this is becoming 0 in previous iteration. This was becoming 0 at t is equal to 5. So if t exceeds 5, this is going to turn positive, right? This will definitely turn positive, and this is going to be the entering variable. Okay, and if this is going to be the entering variable, we will have to find replacement ratio to decide which will be the living variable. So replacement ratio is the ratio between b by k. 6 by 1 by 8 is 48. 12 divided by negative quantity, this allows x2 to be the living variable, right? So x1 will only be the living variable as we are seeing here. So x1 will be replaced by s1, right? So in the next iteration we get the composition of the variable s1 and s2. Their coefficients are 0, and by doing the transformation to make this column 1 0, we get this table. And Cj minus Ej's are 0, minus 10, 0 and 0. Alright. So now we have come to a stage that S1 and S2 are optimal solution. Their values are 48 and S2's value is 24. X1, X2 are 0. Mean the time after 5 weeks has increased to such an extent that the profit per unit of X1 or product A and profit per unit of X2, X1 profit per unit of product A has become 0, and profit per unit of product B has turned negative. So it is not worthwhile to produce product A and product B. We will be letting all our spare capacity of indicated by constraint 1 and constraint 2 to let go west. Okay, so the parametric programming ends here. The collection of the results is demonstrated here. t from 0 to 1, my optimal solution is x1 equal to 36 by 7, x2 is equal to 24 by 7, and as the t varies, z value will change according to this. 480 by 7 minus 144 by 7 into t. And from 1 to 5, optimal solution, as you have seen, x1 equal to 6, x2 equal to 0, and as the t changes in between 1 to 5, z value will be 60 minus 12t. Alright, and from 5 to infinity, the x1 and x2 both will be 0 and z also will be 0. Alright. I hope you have understood this parametric programming, and I have explained it in blocks, different block ways, right? You have the problem in front of you, you have the method in front of you. Now you can practice this problem yourself, and you can practice another problems also. As I said to you in the beginning, we have parameterized our objective function. You can parameterize the right hand side constants also. You can parameterize the coefficients of variables in the constraint, and the approaches which you have learned in sensitivity analysis can be extended to do the parametric analysis in each of the case. Thank you. Thank you very much.